For a vector in the plane, referring to its direction is fairly straightforward. We can refer to the angle made with the positive x-axis that gives us the theta that we have come to know and love. It's a little bit more complicated with vectors in space. We are going to consider direction cosines. Here we're going to consider a vector in space v that has components v1, v2, and v3. And in my mind's eye, this exists somewhere above the second quadrant, and so here are the visual aids for that. And as you recall, there are three basis vectors in R3, I, j, and k. Associated with these vectors are angles. We'll call them alpha, beta, and gamma. And these are angles made that are formed between the vector v and our basis vectors I, j, and k. In other words, if we imagine a plane that contains the x-axis and the vector v, then the angle made in that plane between the two vectors is alpha. Likewise, a plane that contains the vector v and the y-axis would contain the angle beta between the vector v and j. And then finally we can see that this is gamma between basically the angle between the z-axis and v. Keeping in mind that the cosine of theta, generally speaking, is a dot b divided by the magnitude of a times the magnitude of b, if we replace a with v and b with I, then we get that the cosine of alpha is equal to v dot I divided by the magnitude of v times the magnitude of I. Since I is the vector 1, 0, 0, when I find the dot product of I with v, I have v1 times 1 and then two zeros. So the numerator of what we just wrote becomes v1. Since the magnitude of I is 1, it is a unit vector, we end up with that the cosine of alpha is equal to v1 over v. Likewise, the cosine of beta is going to be v2 over the magnitude of v, and the cosine of gamma is going to be v3 over the magnitude of v. These are called the direction cosines. Note that the cosine squared of alpha plus the cosine squared of beta plus the cosine squared of gamma equals 1, which you can quickly verify. Further, if we clear the fraction for each of these equations, then we see we can represent v in terms of its direction cosines as the magnitude of v times the cosine of alpha, comma, the magnitude of v times the cosine of beta, comma, the magnitude of v times the cosine of gamma. And so v can be actually written as the magnitude of v times the direction cosines. Formally, v equals the magnitude of v times the vector cosine of alpha, cosine of beta, cosine of gamma. Dividing by the magnitude gives us that v divided by its magnitude is equal to that vector made with the direction cosines. Cosine of v can then be written as the magnitude of v times the cosine of alpha, cosine of beta, cosine of gamma, which means if we divide by the magnitude of v, we get v divided by its magnitude times that direction cosine vector, cosine of alpha, cosine of beta, cosine of gamma. This confirms that we have a unit vector here per our statement about the sums of the squares of the direction cosines. Expressing the vector v as the magnitude of v times the vector with the direction cosines is analogous to what we might say in v2, where if we have a vector xy, we can express it as r times the cosine of theta, r times the sine of theta, or r times the vector cosine of theta, sine of theta. That vector, cosine of theta, sine theta, is a unit vector. You can quickly confirm that. And expressing it in this way basically says r is the magnitude or the length of the vector, and the angle theta really just gives us a direction. And we have something analogous here, where the magnitude of v gives us the length of the vector, and alpha, beta, and gamma essentially give us a direction in space.